Hi everyone, I'm Yizheng from Tsinghua University. I'm glad to present our work on text entry for head-mounted displays, which use the head as the main modality to input text. This work is also supported by Samsung Beijing R&D Center. Nowadays, head-mounted displays are getting more and more popular, which can support various VR and AR applications. Therefore, an appropriate text entry method should be required by these applications. For example, when doing virtual shopping, one may need to search a specific product. Similarly, when chatting in VR, one can call a friend conveniently by inputting his name. Although it is not certain whether productivity tasks will be supported in the future, we still believe entering short text in such application is practical requirement of HMD users. So let's first look at how text entry is supported in practice for head-mounted displays. This video shows how users input text on HoloLens. To input a letter, the user first moves the pointer over the letter by rotating his head, and then performs a finger tapping gesture to confirm the selection. I'm not sure how many of you have tried with this, but actually this interaction is complained by many users. First, it is not easy to learn the finger gesture. You have to do it clearly and quickly. Second, the depth camera of the HoloLens has a limited field of view. As the user rotates his head, the finger often gets out of the view of the depth camera. Third, raising hand in the air causes fatigue. Usually, user cannot sustain for 2 minutes. Finally, the input speed is low. According to our informal text, the text entry rate was no more than 10 words per minute. A set of multi-modal techniques have been proposed which suppose text entry in VR and AR. We next briefly review them. For touch, recent work allows users to input text on the leg of smart glasses. The achieved input speed was low, under 10 WPM. Head typing has also been explored. However, in contrast to our work, in previous work, the display was physics in the environment. The obtained text entry rate was very even lower, no more than 6 WPM. Gaze is another modality widely employed to facilitate input, especially for people with motor impairment. The problem with gaze typing is the expensive hardware and the visual attention is easy to be distracted by elements on the interface. The final solution is mid-air input. User can input with a single finger or multiple fingers in the air. The text entries was as high as 29 word WPM. However, such solution also suffers from fatigue issues and additional hardware cost. Our motivation of this research is twofold. First, HMD has a unique advantage to support head input, since user can always see the displays as he rotates his head. This is in contrast to previous head typing research, where the display is fixed in the environment. Therefore, it is valuable to exploit head typing techniques on HMDs. Second, head typing on HMDs employ only the built-in sensors of the device, which is low cost and therefore of more practical value. In this research, we explore head-based typing techniques. We have raised some specific research questions. First, is it feasible to type with head on HMDs? For example, do fatigue and dizziness matters? And if it is feasible, how fast and accurate can user type? Finally, what new patterns of head movement will emerge compared to typing with fingers? So here's a preview of our work. First, we propose 3 head-based test entry techniques. Next, we conduct the first study to compare their performance. Then, based on the new pattern's head movements we find in study 1, we improve the algorithms of gesture typing. Finally, we conducted a second study to evaluate the performance of GestureType with the new algorithm. We implement the prototype system on Gear VR and leverage Unity 3D to obtain head rotation and build the interface. To avoid parallax, we render the keyboard 10 meters far away from the users. The keyboard size was determined according to a pilot study. Users find a keyboard with a width of 6 meters most comfortable for wielding and controlling. This yielded a field of vision of 33.4 degrees. We propose 3 head-based typing techniques. They are DwellType, TapType, and GestureType. With all these techniques, users move their head to control the cursor on a virtual keyboard. So let's look at the implementation details of the 3 techniques. DwellType is a hand-field input method. Users select a letter by dwelling over it for a period of time. In a pilot study, we tested a range of time period and find that 400 milliseconds to be appropriate. For TapType, we employ a gamepad to provide the button input. For both DwellType and TapType, we applied a statistical decoding methods to handle the noise of the input. This method is widely used in software keyboard to deal with the fast finger problem. As the basic idea is to compute a word with a maximum probability of the observed input. For GestureType, user press down the button to start the gesture and release it to indicate its end. The system applies pattern matching to convert the gesture into words. Each dictionary word is transformed into a template, which is the lines connecting each letter on the keyboard. Then, the algorithms compute the distance between words and input gesture and find the word with the minimal distance to be the best match. We conducted the first study to compare the performance of the 3 proposed techniques. 80 participants took part in these studies. 6 of them were female. It was a between-subject study, so each technique was tested on 6 participants. Each participant transcribed 48 phrases in 6 sections. Between sections, participants took a 1-minute break. The experiment took about 50 minutes for each user. So here's the test entry rate of the 3 techniques over section. GestureType was the fastest, then TapType, and DwellType was the slowest. Next, here is the subjective feedback. On perceived speed, TapType and GestureType are both significantly faster than DwellType. The score of fatigue is not so high, but acceptable. All techniques are easy to learn. Before the user study, participants familiarize themselves in no more than 3 minutes. Overall, participants preferred TapType and GestureType more than DwellType. We look into more details on how users interact with the 3 techniques. We investigate 3 actions as this table shown. They are default, select, and delete. Default means that the user confirmed the default word in the text field. For TapType and DwellType, it was the literal letters that had been input. For GestureType, it was the top 1 word that has been predicted. Select means the user selects a predict word from the candidate region, other than the default word. For TapType, nearly 75% of the action was select, meaning that users tend to leverage error correction and select a word in the candidate region. These results show that with TapType, participants rely more on the correction ability of the algorithms, rather than selecting that key equivalently. For DwellType, more than more than 90% of the actions were default. That is, participants tend to enter every key of the intended word. This is probably because by dwelling, users look at the letters for 40 milliseconds when confirming selection. Due to this, it was unlikely to enter a wrong letter. For GestureType, the most frequent action was default, meaning that the user's word gesture and the system decode it as the correct intended word. In only 3% of the action, users delete the word they had written in order to input again. This results show that the recognition algorithms perform well. In this study, we find some head movement patterns, which can be used to improve the recognition algorithms of gesture typing. We had two major findings. The first one was users performed more accurately in vertical than in horizontal. The figure on the right shows the point cloud of the distance between gesture and the word template in each x-axis. The second finding was users performed more accurately for the start and end of a gesture. This feature has been found in previous work on smartphone, but it was much more significant here. This inspired us to assign more weight to the start and end of the gesture. According to the finding, we first place different weights on x-axis and y-axis. To do this, we calculate the distance between gesture and word template based on magnanimous distance. Second, we assign 25% to the start and end of the points, and 50% for the mean distance of all middle points. The parameters were determined by simulation. After improving the algorithms of GestureType, we conducted the second study to explore the expert performance with it. 12 participants took part in the experiment. Notice that the only independent variable here was section, because we required users to transcribe the same 10 phrases for 8 times with GestureType. For speed, users can type pretty fast in the first section and finally achieve 25 WPM after 60 minutes of training. It's improved by nearly 50%, and the learning curve seemed not to converge at the end. Based on this result, we argue that head-based text entry is efficient on head-mounted displays. The subjective feedback was generally the same as study 1. In this study, no participants reported dizziness. Most users reported they start to feel fatigue at the 6th section, which was after typing for 40 minutes. It showed that fatigue from head-based typing was acceptable. Users also developed strategies for the algorithm. For example, they find that longer words to be more tolerant to inaccurate gesture, so they perform a gesture faster for longer words. Moreover, expert users can draw a gesture carefully to tell two similar words apart. Take shopping, for example. It was easy to confuse with shipping, so users traverse all carefully to avoid I. We assess the improvement of GestureType based on the top 1 accuracies, which is the percentage of predicting intended word as the best match. In study 2, the accuracies was nearly 85%. To enable fair comparisons, we ran a simulations by testing the algorithms of study 1 with gesture data in study 2. This accuracy was only 74%. It showed that the modified algorithms indeed had a stronger decoding power. So we conclude our research in 3 aspects. First, head typing is a feasible solution for text entry on head-mounted displays. It provides good text entry rate, and users do not feel dizzy when input. Second, GestureType performs better than tab-based typing on HMDs. This is because users do not have to post their head on the intended keys. Finally, head movement during head typing presents unique patterns, which can be leveraged by word gesture recognition algorithms to improve accuracies. So that is my talk. Thanks for listening. I'm glad to answer any questions.
for a few questions. Please use the microphone.
Hi. I wonder, have you compared this your type with the head-mount display on, and also having people typing on the keyboard? And
Keyboard?
Yeah.
Yes, in this, there is some techniques that you can wear a head-mounted display and type in the keyboard. But we think that there is some scenario that we should we maybe have no keyboard and we only have a head-mounted displays like the Samsung Gear VR because it's very variable. So sometimes we will need it to have a short text entry. So maybe it's useful for some time.
Okay. Thanks.
And so I was wondering if you could say maybe a little bit more about how you were measuring fatigue. It seems like having people do this for an hour would be very fatiguing, and having 40 minutes until they felt fatigue seemed like a long time. So what did you use to measure that?
Oh, thank you. It's an interesting question. When we do this research, we find that it is very impressive. That we find that the head movement, the fatigue of head movement, indeed is better than we use the hand in the air, because for some objective. Because when we run the second study, the participants report that they feel fatigue at the sixth section, and we defined that the test entry rate is becoming increase slower in the sixth section, mm-hmm. And in the first sixth section, the learning curve increased very quickly. So we think that. In this, we will feel fatigue.
Okay, so the fatigue was just when they weren't improving anymore, is how you were measuring that? Yeah.
Pardon?
You were saying that it's fatigue when they're no longer improving? Is that what you were just explaining?
So
we can talk offline. That's okay.
That's okay. Thank you.